Welcome to Natural Habitat Adventures Daily Dose of Nature. I'm your host, Sunny Vanderstar. Today's topic is what mass extinction tells us about an evolving planet. And it will be presented by our fabulous NatHab Expedition Leader, Eleanor Edye. Eleanor, thank you so much for being here today and for bringing us yet another fascinating topic that we probably haven't thought about in the last month or so. So this is exciting. Let's dive in.
Wonderful. Thanks, Sunny, and thanks everybody for showing up today. I hope you're having a beautiful day wherever you are. It is a gorgeous spring day where I am here in southern Manitoba, and there's nothing I like better to talk about on a beautiful spring day with the birds coming back and, you know, spring flowers starting to pop up than the extinction of most of life on Earth. So we're going to be talking today about a discrete period of time called the Ordovician mass extinctions, and hopefully putting them in the larger context of our history of life on Earth. Um, I did a presentation some weeks back on our very first mass extinction that we know about, the Great Oxygenation Crisis, and there seemed to be interest in talking more about destruction of all life on Earth. And I like a good disaster movie, the same as anybody else, and I'm really happy to be here and able to talk to you about kind of the next big thing that happened on our planet, um, the Ordovician mass extinctions. So let's kind of dive into what we're going to be talking about. So specifically, when we're talking about is, of course, the Ordovician period. This was a period of time that ran between about 485 to 444 million years ago in the history of our planet. It was a very interesting piece of time because we had a period of time of about 40 million years where we had what was called this Great Ordovician biodiversification event. So it was the period of time in our planet's history where we had the greatest increase in biodiversity that we have ever had, that was then immediately followed by two massive pulses of extinctions that collectively added up to about 85% of all species in the world lost. If you're looking at the screen here, it says 85% of all marine species lost, and that is because life at this time was really restricted to the seas. We'll get much more into this, but in general, the Ordovician was a period of time when life was in the seas and in the oceans. It was a worldwide extinction event, so it wasn't localized to any one place or any one group of species. And it is the world's, it depends on how you divide this up. We can call it the second most severe mass extinction event that we know of in the history of our world, in that we lost about 75% of global species. The Permian mass extinctions, which maybe we'll get to in a future webinar, had more species lost. However, the Ordovician mass extinctions were the fastest in the fossil record. So whatever happened, which we'll again get into, it happened very quickly. So lots of changes in what happened in the planet at this time. Now, as we talk about kind of mass extinctions, we have to address biodiversity as well. If you go out or if you travel and you've looked around the planet, we have a lot of species right now. Have we always had this many species? Obviously not, because we've had these mass extinctions that we're talking about where we've lost a huge number of global species. However, even with those mass extinctions that we talk about, we currently live in the most diverse time that has ever existed in the history of Earth. We have millions of species on land. We have likely millions of species in the ocean as well, and we have not always had this many. I mentioned during the Ordovician, when you're looking for it on this graph here, you can find it. It's the third letter on top. It goes V, C, and O. The O stands for the Ordovician. This was a time where we only really had life in the oceans, but you can see that there was a pretty good increase and then it plateaued for quite a long time, that life in the oceans. But we've had a great diversification of life on land because land has not always been an available habitat for life, which again, hopefully we'll get into in a future webinar when we talk about more mass extinctions and diversification of life on Earth. But in general, right, as we get more species, that begets more species again because of specialization. So for example, if we have a new species of tree that evolves, that then opens up new habitat for insects, fungi, bacteria that may then specialize on that one species of tree. So every new species that we get potentially creates habitat for other species to then evolve into that new habitat. Now, are we only getting new species even though we're living in this time of plenty? Is that all that's happening? No, there is always extinction going on. Whether or not we're talking about mass extinction, we always have what's called a background level of extinction, and we can look at it in the fossil record. We can look at it happening in life as we can observe it. On average, throughout the history of our planets, between 10 and 100 species per year will go extinct. And that's very much an average. It's not a constant rate. This tends to come in big pushes. But matching that background extinction rate is also a background evolution rate. So that when our number of species are staying constant, it's not that we're never gaining any or losing any, it's that we're doing both. We are gaining and losing at the same time. And here, of course, we're talking about not just the fluffy animals, we're talking about fungi, insects, mammals, bacteria, any piece of life on Earth that we can recognize as a species. To keep things in perspective, if we think about all the species that have ever existed on this planet, at least 98% of them are now extinct. So we really only get to see a snapshot of life on Earth during the period of time that we live. And I think that's a really cool reason to look back at all of these things that no longer exist, but probably thought that they were the bee's knees at the time that they existed, just like we do today. So all of these are rough estimates. That's background extinction. Extinction events are different. In a mass extinction, species go extinct at a rate that is much, much higher over a shorter period of time. And we're talking short in the geological history of time. So to define something as a mass extinction, we usually use the numbers about 75% of species lost, at least, over no more than 2 million years of time. So that is our kind of broad definition for when we call something a mass extinction. It's not all lost in 3 years. It's over a geological period of time, but we're talking about a lot of loss. When we look at some of the slides coming up, you're not always going to see these numbers expressed as a number of species lost. Sometimes it's expressed as a number of genera lost or a number of families lost. These types of losses, if we're counting them that way, are even more devastating. If we're talking about the differences between a species and a genus and a family, you can use the analogy of the difference between like a red fox, which is a species going extinct, versus the genus Canis, so all foxes going extinct. So that's at the genus level. Or if we talk about the family level, that would be the loss of all Canidae, so the loss of all dogs. So all dogs, foxes, wolves, coyotes, jackals going extinct. So a species being lost is certainly something to be sad about and to mourn and to think about. But when we look at extinction at the genus level or at the family level, we're talking about a much bigger blow in that case. So just keep that in mind as we're throwing some numbers around. Now, let's move slides here. Let's talk about the 5 mass extinctions that we know of and that you'll usually see discussed as we talk about Earth's mass extinctions. We call them like the big 5, quote unquote, because they are not the only mass extinctions that may exist. They are the ones that we know of. Anytime we talk about stuff in the scientific community, there is always debate, but these are definitely the best known, the most studied, the ones that we have generally good agreement on, while knowing that we may always get more information in the future. If you attended the webinar I did on the Great Oxygenation Crisis, this one is not even listed on the list of the Earth's mass extinctions for a variety of reasons, one of which is that it was a long time ago and we don't know much about it. The scale that we're looking at here, when you're looking at those blips that the arrows are pointing at, these are genera, so at the genus level. So why those drops don't look as dramatic is even as we lose, 75% of species, each of these mass extinction drops represents at least 75% of species, but they usually will represent then fewer genera and fewer families, because at those higher taxonomic levels, we're not losing, all dogs. We might lose all foxes, or we might lose a fox, to continue on with that analogy. How far back are we looking? Well, I said 444 million years to about 485 million years. But I think kind of a way of looking at it even better is that we are going all the way down our rock strata here to the beginning of fossils. So when we look beyond the Cambrian and the Ordovician, this is the time beyond which we didn't really have multicellular fossils. I showed this infographic before. I will show this infographic anytime I can because I love it so much. It's got all of our eras and epochs showing. And the periods, pardon me. So as you look kind of in the middle here, you've got the Cenozoic on top, you've got the Mesozoic underneath, and you've got the Paleozoic. Those stand for current life, middle life, and old life. So we're stepping back here into the Paleozoic, the old life time. We call it old life because the type of life that existed then, it's not that none of those species exist anymore, but they are some of the oldest multicellular life on Earth. And it's not the current assemblage of species that we see. And we are stepping back, not quite to the bottom of this record here into the Cambrian, but into one above it, the Ordovician. Another name for that period of time is the sea without fish, because as we'll see, we're dealing with a land of seas, but not yet at a time when we have evolved fish. And just to give you context, again, within the larger history of the Earth, when we were talking about the Great Oxygenation Crisis the other week, we were talking about a period of time here. Oh, there we go. There's that arrow popping up that occurred back in the Archean, back in the Proterozoic. So back in like the very early life, the start of life, back in the multiple billions of years ago. Now we are talking about when multicellular life exists. We have fossil evidence of that time. We have good rock records of this time. We have jumped into the Paleozoic and into the Ordovician period. So this next big arrow that's pointing here is looking at, again, if 12 o'clock is current time, and we kind of track that clock back, we're already looking at around 11 o'clock on our planet's history. So geologically speaking, this isn't that far back in terms of how long our planet has existed, but there's been an awful lot that has happened in that 444 million years. So let's talk about what the world was actually like at this point. So I talked about lots of water, I talked about sea without fish, I talked about no land species. So this here is a graph of air temperatures. I'm just going to click ahead here so you can see where the Ordovician is. It should just be highlighted in yellow there. And this is looking at changes in average air temperature around the world, kind of over a long period of time through Earth's history. If you look at the Ordovician and you're looking at those temperatures, you'll see that there is a massive shift that happens between the beginning of the Ordovician period and the end of the Ordovician period. And in fact, an expected average drop in global temperatures from 25 degrees Celsius, which is around 85 degrees Fahrenheit, down to 10 degrees Celsius, which is, hard to make those conversions on the fly. Temperatures. Um, if you're looking at what immediately precedes that, the Cambrian period, that was a very even-paced temperature world. So how we divide these periods up are mostly based on assemblages of fossils. So where we see changes in life on Earth, that's where we tend to make those big divisions. That's often matched with big events like this drop in temperature that we see here, but not always. And we'll talk about the differences between the Cambrian and the Ordovician right away. So there is another exciting thing that happens in the Ordovician. It's not really exciting for the purposes of talking about the extinctions, but it's kind of exciting anyway. It's the evolution of land plants. So that happened right around where that arrow occurs, right where we see that drop in temperature. And while you might look at that and say, oh ho, there's a smoking gun, it's caused the temperature to drop, plants moving on to the land. We don't think that there was any linkage there. The land plants that existed in the Ordovician were very small relatives of green algae, probably similar to mosses and liverworts that we have today, and they were very, very restricted in where they were found. So it's cool, it's important, I wanted to mention it where it happens, but it doesn't really have a lot of bearing on what we're actually talking about with species loss. And this here is what the world looked like in the middle of the Ordovician. So this is kind of the middle point of the Ordovician, but the continents and the continental plates were pretty well in this location all the way through the Ordovician. So it was a period of time, as we mentioned, of high temperatures, starting around 25 degrees Celsius, going down to 10 degrees Celsius. To give you context for what we have today, the average global temperature today is around 15 degrees Celsius. So 25 is a lot hotter than what we have now. So it was high temperature. We had high sea levels because there were no glaciers, there were no ice caps. All of that water was just spread out over those continental shelves. And we also had high levels of carbon dioxide. If you look at where those continents are located, they're primarily in the southern hemisphere with very little continental mass above the equator, so in that northern hemisphere. We had a lot of what are called epicontinental seas. These are like we have Hudson Bay today. It's a saltwater sea that sits on top of continental crust. So you really only get epicontinental seas when you have enough water that's not locked up in ice to cover those continents. And in many of these areas, these epicontinental seas, as you can see, were wide-ranging. Like most of what's now North America was covered in the sea, and it would have been anything from knee-deep up to maybe 20 feet deep. So very, very rich habitats. That type of habitat where you see it today tends to have a lot of diversity, a lot of productivity because it's a very shallow ecosystem with sunlight that reaches all the way down to the bottom. And we had a lot of that very spread out. So as you can see, these different continental areas were all the way kind of around the world here. And so we had all of these epicontinental seas that were not connected up with other ones that existed at the same time. We had some tectonic movements at this time, so there was a lot of continental uplift happening. The Appalachian Mountains got their start at this point, so there was some tectonic plates moving around, causing the uplift of the beginning of the Appalachians. And there's going to be some other things that happened throughout that you'll see right away here. This is a very busy infographic, so I just want to kind of take a minute and break it down here. If you look on the left-hand side, it's another view of the way the world was. So now instead of looking kind of flat at the equator, we're looking from the South Pole looking northwards. So you can see that there is a big, massive continent known as Gondwana, which is the current assemblage of Africa and Australia, as well as some other bits in there as well in Antarctica. And then we had those other continental masses kind of more around the equatorial areas. If you look at the right-hand side, we have some graphs, and I'm going to get you to look at the top graph here. That green line that is in that topmost graph represents the number of genera in a particular group called the brachiopods, which we often use as a proxy for the number of species overall. So you can see how the number of genera are increasing throughout this time. And then you get to this blue line on the right-hand side that just kind of does a little boom, a little drop off the edge of a cliff there. This period of time of the rise is that great Ordovician biodiversification event. And that step off a cliff at the end as you hit that blue line there is that mass extinction. As this time was going on, the pink line on that top graph represents atmospheric oxygen. So we're seeing an increase in oxygenation at this time as well. If you look at the bottom graph, you're looking at atmospheric carbon dioxide, which is decreasing. And along with that, the pink line there represents sea surface temperatures. So this was like, overall, look at this. So many things are changing. We have oxygen that's going up. We have air temperature that is dropping. We have sea surface temperatures that are dropping. We have carbon dioxide that is dropping. We have species that are increasing like we've never seen it before, and then dropping. There's a lot going on in this relatively short period of time. When we're looking at those sea surface temperatures at the start of the Ordovician, we extrapolate that the sea surface temperatures would have been around 45 degrees Celsius or more. So we're talking around like 110 or more degrees Fahrenheit. Hot, 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 hot oceans at the surface. Part of this being that it was a hotter world, but likely the bigger part of this being that ocean circulation wasn't as strong as it is today. So instead of that hot water, as it's warmed by the sun, being pushed downwards by ocean circulation, it just stays at the surface and gets to keep heating up and being quite stagnant at those surface levels. Throughout the Ordovician, that 45 degrees Celsius sea surface temperature dropped down to about 25 degrees Celsius. By comparison, today's numbers are an average of about 21 degrees Celsius, which will reach quite a bit higher in our equatorial seas for point counts, but on average, we have sea surface temperatures of about 21 degrees Celsius right now. Just as a quick note, carbon dioxide was way higher than today, almost 8 to 9 times higher, but the sun was weaker. So those higher levels of carbon dioxide did keep it warm, but not as warm as they, for example, would today if we saw those same levels of carbon dioxide, because our sun is now emitting quite a bit more energy than it was at this point. So this is a very, very different world than what we have today. And it was also a world that was going through a lot of changes. Throughout the first 95% of the Ordovician, there were some species that thrived pretty well. Before we got into the Ordovician, though, is where we started to see the diversification of animals overall. And I have to give a quick shout out to the Cambrian explosion. The Cambrian is the period that immediately preceded the Ordovician. And while we had the Great Ordovician Biodiversification Event, or you want to be really cool, you call it GOBI, the Cambrian explosion, also known as the Cambrian radiation, was another period of time where life kind of went wee and just diversified like crazy. Not quite at the same levels as in the Ordovician, but what we saw in the Cambrian was a sudden radiation of complex life. Before this time, we had colonial life, we had unicellular life, but in the Cambrian, things started popping off and we started seeing all of our major animal phyla that we still have today diversified in the Cambrian. There was a lot of wacky body types that got tried out. Most of these animals eventually died off, but they were incredible and they were different than we have today. And it was kind of a period of wacky experimentation. And our ancient ancestors would have diversified at this time as well. There are some places in the world where you can see direct evidence of the Cambrian explosion. Some of the more famous sites include some in Canada, like the Burgess Shale. That's where this photo on the right comes from, where we had a lot of these animals that diversified at this time were soft-bodied, so they didn't fossilize very well. But because of certain conditions that existed, we had these shale, what are now shale deposits, where a lot of these soft-bodied animals were fossilized. And these are cool things that you can actually go see in person if you're willing to do a really big walk up a mountainside. one of the most fun days I've ever personally had. So that's what came right before the Ordovician. In the Great Ordovician Biodiversification event, it wasn't so much that we changed everything from what had happened before, but what we did was kind of take the species and the groups that first diversified in the Cambrian and made them more diverse. So we had diversification at the species level and at the genus level and at the family level. The orders were kind of set, but then we added on more things because they were able to further split and diversify. So a lot of this increase in diversity then occurred kind of within communities that already existed. And they made use of, just like we were talking about, unexploited niches. So just like, for example, that new tree that can then have new insects and new fungi and new bacteria that can survive on it. If you have now had the development of a new type of reef building organism, well, then your reef can now support anything that can live within the reef, and then things that can live within the animals that live within the reef. And it just allowed for this rapid diversification because of this initial starting point, and also because of the way the world was laid out. Because we had those epicontinental seas that were spread pretty far apart. I know a lot of people have heard of the Galapagos Islands and have maybe heard about how biodiversity tends to increase in patchy habitats like that, where we have species that can be separated and then have time to develop on their own. When we separate those seas out, that's the same kind of thing that happens. So we had a lot of new habitats and then a lot of new ecological niches open up within those new habitats. So these communities that then diversified within the Ordovician were ecologically complicated. There were new life habits that appeared. So we had things like deep deposit feeders, we had mobile carnivores, we had open water feeders, we had a huge diversification in carnivores especially, and in predatory animals. In the Cambrian, the earlier one, most of those communities live close to the bottom of the ocean and those epicontinental seas, so the seafloor communities. But into the Ordovician, they were able to diversify into different strata. So the bottom of the seafloor, midway up, at the top. So a lot of increase in community types as well. Now, some of the species, or not so much the species, but the groupings we'll throw up right away, many of these still exist as live specimens today. They haven't all gone extinct, but they no longer have that same level of dominance that they did back in the Ordovician. So I just want to run through a handful of these organisms that you would have seen had you been there in the Ordovician and been able to slap on a scuba tank and a mask and look around these marine habitats, because that's where the life was. So we had the bryozoans. Bryozoans are, take the name and break it down, it means moss animals. So they are animals. They are a calcium carbonate casing animal, similar to our corals today. The Ordovician was the first time that we started to see calcium carbonate be used as a structural building block. And the bryozoans, together with the next animals we'll look at, the sponges, made up the majority of the reef systems during the Ordovician. There were corals, and we'll look at those right away too, but they were not nearly as ecologically important as the bryozoans and the sponges were. So you can see a living one there on the left and a fossil on the right. Here are some sponges, again, living on the left and then fossil on the right. These are very primitive animals, but primitive doesn't mean that they're not important. In fact, they're some of the most important animals from this period of time. Some of them have low levels of motility. Most of them just kind of sit there and filter feed. They're not complex organisms, but they're very good at what they do. They have a constant water flow through their bodies to obtain food because they're filter feeding. as well as getting their oxygen that way. And they provide a habitat for a lot of other things, again, just like we're seeing, that live within as well as around them. Like I said, there was coral at this time. There were two main types of coral, rugose coral and tabulate coral. Neither of these types of coral exists today. There are newly evolved types of coral. Obviously, we still have coral reefs, but they're not directly related. They're not closely related to the coral that existed within the Ordovician. In fact, the vast majority of this coral went extinct during the set of mass extinctions. So rugose corals could grow independently as horn corals, or they could also grow as a colony. All solitary rugose corals were extinct by the end of the Ordovician. No solitary corals made their way through that extinction. There were the tabulate corals. These no longer exist at all. They went extinct, not at the end of the Ordovician, but many species did. You can see that they're superficially quite similar to today's corals. They still have that calcium carbonate skeleton. They still have pores. They would still have little polyps that live within them. But it's not quite the same as today's corals, and they are within the larger phylum, but they are not closely related to corals today. We have the brachiopods. Brachiopods are animals that still live, but they are nowhere near as diverse as they are, or as they were back then. At their peak, we know of at least 30,000 species of brachiopods. There are about 300 species that still survive today. You might look at this and say, well, that looks like a clam. What's so special about that? Brachiopods and bivalves look so similar, and they are ecologically very similar. But like a number of things in life, what you look at first isn't necessarily the truth. Brachiopods are not directly related to bivalves, bivalves being things like clams or mollusks, for example. I know they look the same, but they are they are different, believe it or not. This is a living one there. This is a lingulata, belongs to the class of brachiopods. Lingulata has existed unchanged for about 400 million years, which is pretty crazy. We can see evidence of that same genus within the fossil record. But most brachiopods have been lost to time. The crinoids are a really fun one, I think. They're also known as sea lilies or feather stars. They do still exist today, mostly like what you can see on the left. In the Ordovician period, most of the crinoids look like what we see on the right. So these belong to the same group as the sea cucumbers and sea urchins and sea stars. They are fivefold symmetric, just like all the rest of them. And during the Ordovician, they were primarily stalked organisms. So they are animals, but they kind of look like flowered. And some of them were up to 65 feet long. So they were a big part in having that different levels of habitat within an ecosystem. So they were able to cover a large area, and some of these were very, very big organisms. We still do find them today. Like I said, they're primarily detritus feeders, and there's about 80 living species of these today. A fun one, I think, is the conodonts, because these are one of the first vertebrates that we know of. So while they may not be our direct ancestor, jury's out on that one, they are kind of one of our earliest relatives. They're extinct now. They were jawless vertebrates. For a long period of time, all we knew them from was the fossilized bits, so the tooth elements that you can see on the left. And then the fossil reconstruction is on the right there. So we think that they looked like eels. I'm going to show you an artist's interpretation of what they looked like. Here it comes. So slightly terrifying. Good thing they were only about 10 inches long at the most. So they were obviously predators. They lived for a very, very long time in the oceans, but did go extinct, not at the end of the Ordovician, but before today. I think one of the cool things that we think of often in the Ordovician were the cephalopods. So today the cephalopods include things like octopuses, squid, cuttlefish, nautiluses. Um, the Ordovician was really the great age of the cephalopods. They tried out so many different body types. They were huge, they were small, they swam in the ocean, they filter fed on the bottom. They were very diverse and very, very widespread. And I think one of the neat things to think about with cephalopods is perhaps we know of octopuses and squid as being very intelligent today. We don't know what the intelligence of a cephalopod 400 million years ago was, but perhaps you can imagine this period of time being when there may have been intelligent life roaming the oceans. One of everybody's favorites, I think, as well, are the trilobites. So these are probably one of the most historic, most famous prehistoric animals, if you take out dinosaurs. So they are crustacean-like animals that did have a segmented exoskeleton. They were very, very successful within the Ordovician, over 17,000 species known from the fossil record. They range in size from just over a millimeter up to over 70 centimeters long, so quite large as far as these kind of organisms go. The biggest one that we know of was actually found on the shores of Hudson Bay, just outside the community of Churchill, where some of you may have been to see polar bears or beluga whales. This is the biggest known trilobite to have ever been found so far, at least as a complete fossil. And when you come up to it, you can imagine this thing crawling across the seafloor. This was likely a bottom feeder, not a swimmer. But it was found in 1999, and it's 28 inches long, which, okay, let's put things in perspective. I know it's not a Tyrannosaurus Rex, but it is a very, very big, complete fossil from a very long time ago. So that gives you a little kind of glimpse into what the Ordovician seas looked like. I haven't talked about plants because probably all we're talking about at this point is green algae and blue-green algae. But just take a moment to appreciate all these things, because we're next going to talk about how we lost the vast majority of these species. As we talk about how we lost them, I want to talk just really briefly on how we know how we lost them, because I just said how far back we're looking. There is still very good fossil evidence from this time, and in fact, there are some very famous rocks that date all the way back to the Ordovician. Probably the most famous place that you can go to see Ordovician era fossils is Anticosti Island, which would have been a reef during the Ordovician and has remained intact, untouched by tectonic action over that 444 million years. It's right at the mouth of the St. Lawrence River. It's a biggish island, hard to get to though. Very few people live there, and most of this site is under UNESCO protection as a World Heritage Site and also under protection as a national park. The fossils that you can see there represent an unbroken period of time going all the way through the mass extinction. So a lot of research has been done at this particular location looking at changes on this ancient reef. And you can just see like the piles of fossil brachiopods there are just incredible. And it's definitely on my life list to try to get myself to this place. I highly advise that you look up images of this island. It is just completely otherworldly and chock full of fossils. We do see fossils in other places too. So even if we just look at North America, a lot of these epicontinental seas are now, of course, above water because we've had a sea level drop. But if you look at North America there, anything that was kind of covered by an epicontinental sea during the Ordovician likely had fossils that were laid down at that time. And the map on the right, all of those purple markers there represent where the Ordovician is kind of the dominant exposed rock form on the ground. So there's certainly some within the southeast of the US, and there's quite a bit in the area that I live in, which is Manitoba, especially along the Lake Winnipeg area and then up along the Hudson Bay coastline where that giant fossil trilobite came from. This is some of the rock that you can see, and you may have already interacted with some of these fossils from the Ordovician that were collected from Manitoba, because it's a very famous building stone that is used all around the world. This is a particular kind given the brand name Tyndall stone because it's collected very close to Tyndall, Manitoba. It's chock full of fossils. It is a combination limestone and dolomite, highly, highly prized as a building stone. If you have visited the Canadian Parliament buildings, the Legislative Building in Winnipeg, the Canadian Museum of History, the Empress Hotel in Victoria, the Banff Springs Hotel, you will have seen rock collected from the Ordovician that was full of fossils. We have it as a prominent building stone in Manitoba, especially because it doesn't need to be shipped very far, but it is highly, highly prized, and you can find it around the world. So there's a lot, what I'm saying is there's a lot of evidence. It's not like what we were talking about with the great oxygenation crisis where we have to use a lot of secondary evidence. We have direct fossil evidence of this time. So let's move ourselves into the extinction. Like we said at the beginning, about 85% of all species went extinct. Obviously, what the extinction did was mark the end of that period of time known as the Ordovician biodiversification event. This event was global. Two of the groups that were hit quite notably hard were the trilobites and the brachiopods, neither of which went extinct as a group, but many of the species within those groupings went extinct. Where we particularly saw losses around the world were not in individual taxonomic groups. So we didn't see a loss of all brachiopods. We didn't see a loss of all trilobites. We didn't see a loss, well, we did see a loss of all solitary corals, but we didn't see a loss of all corals. What we did see, though, were major, major losses in endemic groups. So species that only existed in certain small areas. We didn't see losses of widespread species or widespread groupings. Yeah, our nautiloids were hit hard. Most things were hit hard. It was just that the trilobites and brachiopods were hit hardest. This extinction is generally agreed to have happened in two separate pulses. And those pulses come back to that blue line that kind of stretches across the right-hand side of these graphs here and has the label Hernantian on it. This Hernantian stage represents at the beginning of the Hernantian a pulse of extinction and then another pulse of extinction at the end, about 1 million or so years apart. So that is a period of time that is very geologically close, but still far enough apart to distinguish. The communities between the beginning pulse and the end pulse are distinct and different than all that existed before and after that time, and they are collectively known as the Hernantian fauna. Essentially, what we're looking at here is a pulse of extinction caused by a massive glaciation event, followed by a second pulse of extinction as that glaciation event resolved. This is the current best thinking on this. We're in general agreement about this. It's always good when we have decent consensus among the scientific community. So during this time, we have this global cooling. The cooling event, if you recall, was happening over a long period of time, but that cooling was initially probably actually helping to drive biodiversity increases. Cooler is often, like not cold, but cool, opens up a lot of possibilities for different niches, for different habitats, for specialists for warmer seas and specialists for cooler seas. But then when we had glaciation, that kind of makes things different again. So we had worldwide changes in that temperatures dropped overall. Sea levels dropped, probably similar to what we saw during our most recent glaciation now in the last 2 million years, which is about a 100 meter to 150 meter drop, up to maybe 400 feet. That would have completely exposed all of those epicontinental seas. So all of that habitat, our nexus of all of that evolution, just dried up completely. I also mentioned how we saw those really high ocean temperatures and how they dropped as time went on. This likely also meant that we had some severe changes in ocean circulation. So ocean currents become stronger, more similar to what we see today. That sounds great, right? We're moving that heat around, but that means that we're then also cooling off the water in certain areas and warming it up in areas and bringing oxygen and moving oxygen out of the system. So basically, you're changing the way that global circulation worked. Yeah, but really that entire set of habitats that was those epicontinental seas disappeared. And there was nowhere for species to potentially migrate to. So this was our first flush of extinction, right? We lose our epicontinental seas. Our shallow sea environments was gone. Our continental shelf environment was probably gone as well. Some of our deep water locations that suddenly got a flush of oxygen changed as well. And we saw this big change in the way the world worked, essentially. And we moved into this very short-lived period of time where we had the Hernantian flora and fauna. So the animals that thrived and were able to survive in this new set of conditions. It wasn't that we lost all species right away. During that first push, we lost the ones that couldn't adapt or that weren't adapted to the new conditions. We have this new fauna that exists. And then a million years later, we have it rewarm and that glaciation disappears again. So why did this change all happen so quickly? Well, just like really quickly, we could do a whole webinar just on this. Ocean circulation could have started changing. We think that glaciation may not have existed as a single pulse, but as multiple pulses that existed throughout the end of the Ordovician. We talked about how there was so much carbon dioxide at that time, but it was starting to drop at the same time that we were having a mountain building event with the Appalachians. There was a lot of tectonic activity at this time, and tectonic activity is often associated with volcanic activity. Volcanic activity tends to release things like carbon dioxide into the atmosphere and allow for warming. But once that volcanic activity stops, you have all of this new rock. And part of the rock cycle is as it breaks down chemically, it actually removes carbon dioxide from the atmosphere. This is actually often called like Earth's thermostat. So when you build new rock, it removes carbon dioxide from the atmosphere via weathering. And then we get that carbon dioxide being deposited back into the oceans, which it can then be used for either as for our animals that live within the ocean and require carbon for their skeletons, for example, or is simply deposited as a sedimentary rock at the bottom of the oceans. So we don't exactly know why glaciation happens so fast in and out, but we see activity like this throughout the history of Earth. We've seen it very recently. We know that mountain building initially tends to cause a period of warming and then tends to cause a period of cooling. So anytime we see big evidence of volcanism, of a lot of mountain building or volcanic activity, that we're likely going to see global cooling afterwards as that new silicate rock is weathered. So as that climate rewarmed again pretty quickly, like again, quickly within geologic terms, anything that ended up surviving that first pulse of extinction was like, hey, this new world is one I can live with. Well, it changed again. And so any of those species that survived, many of them were then in line for that next round of extinctions. The second pulse didn't hit those continental ecosystems because there weren't any left. They were all gone. The deep water ecosystems likely changed back to a low oxygen environment. So it removed any new fauna that was able to survive that higher oxygen environment. Now there were likely more oxygen poor waters moving up onto the shore, so nearshore environments were hit. And ultimately, like this was a very short glaciation, only about 1 million years. So there was just no time for organisms to adapt and diversify within those new habitats. But there are some really interesting things came out of this extinction. Ultimately, that second pulse of extinctions marked the end of the Ordovician and takes us into the new period of time called the Silurian. What we saw was a recovery during the Silurian, but not at a rate that we could ever see like we saw in the Ordovician ever again. We've never seen that same level of diversification so quickly. What makes this one of, I think, the more interesting mass extinctions is that it was fast. So fast that things almost didn't have time to adapt to new conditions. And that when you came back in the Silurian is really, really similar in terms of the ocean conditions and the atmospheric conditions to the Ordovician. So those animals that did manage to survive from the initial Ordovician period did just fine in the Silurian. We didn't see a whole host replacement of species with something else like we did after some of our other mass extinctions. We're like, okay, we took everything out. The world is different and a new group of species are surviving and thriving. This was like, the world was like this. We changed it a lot for a short period of time and then the world went back to what it was. And so the things that did survive did pretty well and were able to kind of re-diversify. So while individual species were hit hard and even some genera, so at the genus level, we didn't tend to lose a lot of families, right? We kept trilobites. We lost a lot of species, but we kept trilobites as a whole. We lost a lot of brachiopods, but we kept brachiopods as a whole. We lost a lot of sponges, but we kept sponges as a whole. So it's, where are we here? And I'd just like to give a shout out here to the sponges because the more we learn about some of the ways that we can look at our own world today. What we can learn from looking back at the Ordovician is that lots of rapid changes are bad news for biodiversity. It makes sense, but we can look back in the fossil record and see it. Even if you end up where you were before, cycling through those rapid changes is going to end up losing you a lot of species. It was a time when, and we can know that what we can look back on today is looking at species that were specialized to a certain set of conditions or a certain habitat that worked against them. So it was those widespread species, the generalists who could survive in multiple conditions that were able to survive the extinction event and then go on to do just fine in the Silurian. We also learned that what survives matters for the recovery of biodiversity. One of the groups that did okay through this time were the sponges. And in fact, when we look at historic records and fossil records, sponges seem to have saved the day for a lot of our underwater communities. They worked as stabilizers, they worked as habitat for other species, and likely were allowed those organisms and those ecosystems to recover faster because they were there. Now, today, are sponges that important? I mean, maybe it depends what happens, but we can look overall at those keystone species, those species that help create habitat are the ones that can help you recover after a massive disruptive event like that. Today, perhaps it might be something like beavers, because without beavers, North America would not have the type of ecosystems that it does. We wouldn't have the same kind of animals that it does. If we lost beavers in a mass extinction, or if we just killed them all off like we tried to in the fur trade, North America would not look the same and we wouldn't have the same species in it as we can with the presence of beavers. So there certainly are keystone species today. We know what some of them are, but we don't really have necessarily a good idea about looking into the next millions of years, what those ultimately important species will end up being to preserve biodiversity on a large scale. We also learned, though, that recovery for ecosystems can be relatively fast if the changes to these ecosystems are short-lived and some animals survive, right? And if we think about, again, making an analogy for today, if we go through a mass extinction and we were to lose all species of bears, so we lost the entire Ursus, the genus Ursus, it might be a while, it might be millions and millions of years before anything bear-like were to evolve again. But if you keep one bear species, that one bear may be able to radiate into different habitats and then diversify into new species of bears again. So that was kind of what happened at this time. We lost a lot of stuff, but we didn't really lose any big groups. So that while the Silurian wasn't a very diverse time, a lot of them were like not heavily specialized organisms, we had a functioning system. We had a functioning planet again relatively quickly because many of those clades were able to survive this mass extinction event. So we'll leave us with that set of knowledge. And I know I've left it down right to the wire. I'm sorry, I have a habit of doing that. But I'll leave a few minutes for questions here and over to Sunny for that.
Thank you, Eleanor. We have a lot of questions, but let's see. There's a few that overlap. The general question, given this topic, is what is your opinion about where we are now? Specifically, the decreasing levels of bees. Is that indicating anything to you, or are we headed for another mass extinction event? These are loaded
Yeah,
questions. That's sort of what the theme
it
is.
is it's a loaded question. It's not a question that we have consensus about, is what I have to say. When we look at, you can Google, are we in a mass extinction right now? And you will not get consensus among the answers. There are a lot of pieces of evidence that point towards us being in a mass extinction. When I talked about background levels of species loss, would I say like 1 to 10 species per million species per year? Well, we're probably looking at about 30,000 species per year right now. That is way, way above historical norms. However, what we don't tend to see yet, in our time is massive loss across the board, right? Humans have had a big impact on things that are big and things that are noticeable to us. We haven't necessarily had as much of an impact on species all the way down the taxonomic levels. So might we be able to call this a mass extinction in 100 years or 1,000 years or 1,000,000 years? Yeah. If we continue these levels of loss, probably. Could we qualify it as this right now? By what we set kind of as how we define a mass extinction, we're not able to say that yet, but we can certainly say that we're not moving in a good direction for protecting species diversity on our planet.
Okay. I think we have time for one more. On the map that you showed before the Silurian, it shows many subduction zones, but no spreading centers. Were there any? And if so, where were they?
Oh, you know what? That is a great question that I have not looked up. However, if you have subduction, you must have spreading. And I think the majority of the spreading, just from thinking about where the plates were at this point, would have been within mid-oceanic zones, similar to what we see today. So if you think about our like the Mid-Atlantic Rift and places where we see that seafloor spreading, it is on the seafloor. Eventually, we would go on to see the breakup of Gondwana through spreading zones, but that was not at this point in time. So I'm going to take a wild guess and assume that all of the spreading zones or all of the major spreading zones were within the oceanic areas at this point in time.
Okay. Sounds good to me. We'll go with that. Well, thank you again. I just want to echo some of the comments of people who are sharing that they just absolutely love your webinars and will get up bright and early in different parts of the world to hear you share your knowledge. So thank you again. I'll hand it back to you for closing comments.
That's very kind. Thanks, everybody. And thank you for showing up today or for showing up later on if you're watching a replay. I've always really enjoyed, learning about the Earth. And I think that we are blessed to live in this beautiful time of biodiversity, but it always behooves us to look back and to see what came before us, is to really think about our larger place in the history of the world. And sometimes whether I'm having a good day or a bad day, it's nice to remember that we're all ultimately blips in a larger worldwide system. So tune in later and maybe we'll do another mass extinction. There's always another one to talk about.
Thank you. I want to thank everybody who tuned in. Please join us again next week for our next Daily Dose of Nature. You can check out next week's lineup, including registration links, on our website at nathab.com/webinars. We did record today's presentation, and we will have the replay available on our website soon. With that, I'll conclude the webinar. Have a wonderful day, everyone.